I am Rajesh Tangella, Department of EEE, Vignan Sinhala Institute of Technology and Science for Women. In the last lecture, I explained about the nominal T method of medium transmission lines. In this lecture, I am going to explain about nominal pi configuration of medium transmission lines. See the equivalent circuit for nominal pi. The difference between nominal T and nominal pi is there we have taken the total capacitance which is localized at this midpoint of the transmission line, but here in case of nominal pi we are taking the total capacitance. We are dividing the total capacitance into two halves. One half is taken at the sending end and second half is taken, that is localized at the receiving end, and the total series impedance is taken in between these two. So in this way it forms the pi shaped circuit. That is why it is also called nominal pi circuit. See the parameters here. Vs is the sending end voltage, Is is the sending end current, and R is the total resistance, XL is the total reactance, IL is the current flowing through that middle section, and VR is the receiving end voltage, IR is the receiving end current, and IC1 is the charging current flowing through the capacitance at the receiving end, and IC2 is the charging current flowing through the capacitance at the sending end, and cos pi R is the receiving end power factor, and cos pi S is the sending end power factor. So in this way we can draw the equivalent circuit for nominal pi configuration of medium transmission lines. And next, if you draw the phasor diagram, see here, first I am taking the VR as reference. So VR as reference, see that OA, so VR is taken as reference. For VR we need to add IL into R plus JIL into XL, so that we will be getting that sending end voltage Vs. So in order to draw this IL into R and IL into XL, first we need to draw IL. For that IL, see the equivalent circuit, you can get that IL as by applying KCL at the receiving end side. Your IL equals to that IC plus IR, IC1 plus IR. So IL will be obtained by adding IC1 plus IR. So we need to draw IR and IC1 first, so that we will be getting IL. So IR we can easily draw that. Here we are taking the load is of lagging load. That is why your IR receiving end current will be lagging with respect to receiving end voltage VR by some angle phi R. So IR is drawn in that way, which is lagging with respect to VR by phi R. From the tip of IR we need to draw IC1. Here how to draw IC1? See the circuit. IC1 is the current flowing through capacitance C by 2, which is at the receiving end, and voltage across that capacitance is VR, so that your IC1 will be leading with respect to VR by 90. That's why here IC1 is drawn which in perpendicular to VR, which is leading with respect to VR by 90 from the tip of IR. So by adding this IR plus IC1 we will be getting that IL. So after drawing IL, now from the tip of VR, see the phasor diagram, from the tip of VR, by adding IL into R by 2, which is the resistive drop which will be in phase with IL, and IL into XL by 2, which is the reactive drop which will be leading with respect to current IL by 90, and this VR plus IL into R by 2 plus IL into X by 2 together gives the total supply voltage Vs, which is a phasor of OC. So OA, which is VR, plus AB, which is IL into R by 2, IL into R, and BC, which is IL into XL. Now VR plus IL into R plus IL into XL together gives that sending end voltage Vs. So see the equations also. IL equals to IR plus IC1, which is obtained by applying KCL at the receiving end, and sending end voltage Vs equals to, just apply KVL for that loop, Vs equals to VR plus IL into Z. VR plus IL into Z means R plus JXL. Now IC2 is the charging current flowing. Of course here we need to draw IS also. So how to draw IS? Just apply KCL at the sending end. Your IS will be equals to sum of IC2 plus IL. Already we have drawn that IL. And already we have drawn that Vs. Now how to draw this IC2 means, see here, IC2 is the current flowing through capacitance C by 2 at the sending end, and voltage across that is Vs, so that your IC2 will be leading with respect to Vs by 90. In that way, this IC2 is drawn from the tip of IL. From the tip of IL, it is drawn in perpendicular to Vs, so that it will be leading with respect to Vs by 90. So now this IL plus IC2 gives total current at the sending end, which is Is. So Is equals to IC2 plus IL. Now the phase angle difference between Vs and Is will be your phi s, sending end power factor angle. If you draw the equation for this IC2 equals to J Vs into omega c by 2, J Vs into Y by 2, total susceptance by 2, or omega c by 2. Now sending end current is Is equals to IL plus IC. Based on these equations and phasor diagram analysis, now let us solve a problem. A 3-phase 50 Hz 150 km line has a resistance, inductive reactance and capacitive shunt admittance of 0.1 ohms, 0.5 ohms and 3 into 10 power minus 6 ohms per kilometer per phase. All the parameters are given per kilometer per phase. If the line delivers 50 megawatts at 110 kV at 0.8 power factor lagging, determine the sending end voltage and current Vs, Is we need to find. Assume nominal pi circuit. So this is the given data. First let us write the given data. Circuit is also mentioned for nominal pi configuration. Given that resistance per kilometer is given as 0.1 ohms. Now as the total length is 50 kilometers, 150 kilometers. So 0.1 into 150 gives the total resistance, which is 15 ohms. In the same way, the total reactance will be 0.5 into total length of line is 150, which gives 75 ohms. Now the total admittance susceptance Y equals to 3 into 10 power minus 6 into 100, 150. So which gives 45 into 10 power minus 5 Siemens. So these are the parameters for transmission line. Now receiving end voltage is given, which is of line value. By taking by root 3, we will be getting the phase voltage as 63,508 volts. Now the receiving end current IR can be obtained by taking P by root 3 VL cos phi. We know that receiving end power equals to P equals to root 3 VR IR cos phi R. From this IR equals to PR by root 3 VR cos phi R. PR is 50 megawatts, 50 into 10 power 6 by root 3 into that VR is 110 kilovolts, 110 into 10 cube, root 3 VL line voltage we need to write into 0.8. So which gives 328 amperes. Receiving end current IR. After getting IR, as cos phi R is given 0.8, from the sin phi R can be obtained as 0.6. Now let us start the analysis. VR is taken as a reference, which will be VR plus J0, so 63,508 volts. Now your receiving end current IR becomes I into cos phi R minus J sin phi R, which is 328 into 0.8 minus J 0.6. So which gives 262.4 minus J 196.8 is your receiving end current in rectangular form, or else you can write in polar form directly as IR at an angle minus phi R. You can do in both ways. Now the charging current at the load side is IC1 equals to, see the circuit, charging current at the load side, that is current flowing through capacitance at the receiving end side, is IC1 equals to VR into J Y by 2. So VR is 63,508 into J, Y means 45 into 10 power minus 5 by 2. So which gives J 14.3 amperes. Now line current IL can be obtained by simply applying KCL at the receiving end. IL equals to IC2 plus IR. So IR is calculated and IC2 is calculated. By adding those two, IL will be obtained as 262.4 minus J 182.5 amperes. Now sending end voltage Vs will be equals to, just apply KVL for the loop, Vs equals to that VR plus IL into Z. So VR is 63,508 plus IL is now calculated, which is 262.4 minus J 182.5 into that Z is R plus JXL, that is 15 plus Z 75. So by adding this, your Vs equals to 82,881 at an angle of 11.47 degrees volts, which is in polar form. Now if you want to find the line voltage magnitude, just by multiplying with root 3, which will be obtained as 143.55 kilowatts. Now charging current at the sending end, that is IC2, will be J into Vs into Y by 2. The voltage across that is Vs into Y by 2. Now 81,131 plus J 16,942.5, which is Vs into J 45 into 10 power minus 5 by 2 Y by 2. So which gives a charging current at the sending end, that is IC2 as minus 3.81 plus J 18.25 amperes. After getting IC2, now we can find the sending current, that is IS equals to IL plus IC2, which is obtained by applying KCL at the sending end. Now IL is already obtained, which is 262.4 minus J 182.5 plus IC2 is now obtained as minus 3.81 plus J 18.25. So together gives the total sending end current as IS equals to 258.6 minus J 164.25 amperes. So in polar form, which gives 306.4 at an angle minus 32.4 degrees amperes. Now if you want to find out the sending end power factor, just take the cos of phase angle difference between that Vs and Is. That means cos of that phase angle difference between Vs and Is is 11.47 minus 32.4. In that way you can find the sending end power factor also. Let us solve one more example based on this. A 100 kilometers long 3-phase 50 Hz transmission line has the following constants. Resistance per phase per kilometer is 0.1 ohms and reactance per phase per kilometer is 0.5 ohms and susceptance is 10 into 10 power minus 6 Siemens. If the line supplies a load of 20 megawatts at 0.9 power factor, lagging at 66 kV, calculate sending end power factor, voltage regulation and transmission efficiency. So we are asked to find cos phi as voltage regulation and transmission efficiency. So let us write the given data first. Total resistance will be 0.1 into total length of the line, that is 100, which gives 10 ohms. In this way total reactance will be 0.5 into total length of the line 100 kilometers gives 50 ohms. And total susceptance is 10 into 10 power minus 6 into 100 gives 10 into 10 power minus 4 ohms Siemens. And receiving end voltage per phase will be obtained by taking by root 3, line voltage by root 3, which gives 38,105 volts. IR can be obtained by PR by root 3 VL cos phi R, which is 195 amperes. Now VR is taken as a reference, which is 38,105 volts. Then IR will be IR into cos phi R minus J sin phi R, 195 into 0.9 minus J 0.435, which gives 176 minus J 85 amperes. If you find the charging current at the receiving end, IC1 will be VR into Jy by 2. So put the values of VR and Y over there, you will be getting IC1 charging current at the receiving end, and line current at the line current will be IL equals to, apply KCL at the receiving end, IL equals to IC1 plus IR. IR is already calculated, IC1 is already calculated, find IL. So which is 176 minus J 66 amperes, and sending end voltage Vs equals to VR plus IL into Z. VR is already given, IL is calculated, Z is already given, put those values, then Vs will be 43,925 at an angle 10.65 degrees volts, and the charging current at the sending end will be IC1 equals to J Vs into Y by 2. So Vs is now calculated into Y by 2, so gives IC2 as minus 0.4, minus 4 plus J 21.6 amperes. Then applying KCL at the sending end, IS will be IC1 plus IL. So putting IC1 IL values, which gives IS as 177.6 at an angle minus 14.5 degrees amperes. In this way we can find the Vs and Is. If you want to find the total sending end power factor angle, first theta1 will be the angle between VR and Vs, which is 10.65 degrees, and theta2 will be the angle between VR and Is, which is minus 14.5 degrees. Phi s will be sum of theta1 theta2, which is 25.15 degrees. Of course we can also find this sending end power factor angle as by simply taking the phase angle difference between that Vs and Is, that some 10.65 degrees at Vs and that minus 14.5 degrees at the Is. So 10 minus 14.5 degrees gives 25 degrees. In that way also we can find phi s. After getting phi s, by taking cos of phi s, we will be getting sending end power factor. So voltage regulation will be Vs minus VR by VR into 100, which gives 15.27%, and transmission sending end power will be 3 Vs Is cos phi s. 3 into Vs is 43,925, sending end current 177.6 into sending end power factor 0.905. So gives 21.18 megawatts, which is the sending end power. By taking the ratio of receiving end power by sending end power, we will be getting the transmission efficiency as 94%. Thank you.